What's the coldest thing you can think of? Maybe a harsh winter in Antarctica, or a scoop of liquid nitrogen. Well, today we're going way, way colder. We're diving into the mind-bending world of absolute zero, the ultimate limit of cold in our universe. So, what exactly asterisk? Is asterisk absolute zero? It's 0 Kelvin, or minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. But it's more than just a number on a thermometer. It represents a fundamental state of matter. You see, temperature is really just a measure of motion. The atoms and molecules all around us are constantly jiggling, vibrating, and zipping about. The hotter something is, the more energetically they move. A hot cup of coffee has atoms buzzing around like crazy. A block of ice has atoms that are still vibrating, just much more slowly. So, if you keep cooling something down, you're essentially slowing down this atomic motion. You're removing more and more of their kinetic energy. Logically, you might think that at some point, you'd reach a state where all atomic motion completely stops. That point is absolute zero. It's the theoretical temperature where all classical motion of particles would cease. It's the ultimate stillness. But here's where things get really weird. Thanks to the bizarre rules of quantum mechanics, the universe, it turns out, has a fundamental problem with standing completely still. Enter the Heisenberg uncertainty principle. One of its core ideas is that you simultaneously know a particle's exact position and its exact momentum. If a particle were to stop completely at absolute zero, its momentum would be precisely zero. This would mean you'd know its momentum perfectly, which, according to the uncertainty principle, would make its position infinitely uncertain. The particle would essentially have to be everywhere at once. To avoid this paradox, particles can never truly stop. Even at absolute zero, they retain a tiny, residual amount of motion. This is called zero-point energy. It's the absolute minimum energy that a quantum system can possess. Think of it as a faint, perpetual quantum hum, an eternal vibration that the universe insists on maintaining. So, even at the coldest possible temperature, the universe is never truly, completely still. Now you might be wondering, have we ever actually reached absolute zero? The short answer is no. And according to the third law of thermodynamics, we never get. This law essentially states that as you get closer and closer to absolute zero, it becomes exponentially harder to remove more heat. Each step requires more and more energy. Reaching absolute zero would require an infinite amount of work. It's like trying to reach a finish line that keeps moving away from you the faster you run towards it. The universe has a built-in speed limit for cold, but that hasn't stopped scientists from trying to get as close as humanly possible. In specialized labs, using techniques like laser cooling and magnetic trapping, they've achieved temperatures that are astonishingly close. We're talking fractions of a billionth of a degree above absolute zero. And when they get things this cold, matter starts behaving in ways you wouldn't believe. It enters neo-exotic quantum states. One of the most famous is the Bose-Einstein condensate, or BEC. ABEC is what happens when you cool a cloud of certain types of atoms, Kayid bosons too, just a whisper above absolute zero. At this extreme temperature, the quantum weirdness takes over. The individual atoms lose their separate identities and start to overlap. Their wave-like properties merge, and the entire group of atoms begins to act as a single, massive superatom, all described by a single quantum wave function. Imagine a crowded dance floor, where everyone is doing their own thing. That's a normal gas. Now, imagine the music changes, and every single person on the floor starts performing the exact same dance move, perfectly synchronized, moving as one entity. That's a Bose-Einstein condensate. It's a collective quantum state of matter, visible on a macroscopic scale. Creating these BECs has allowed scientists to directly observe and study quantum phenomena that were previously just theoretical. But the weirdness doesn't stop there. When you cool liquid helium down to about 2 Kelvin, just a couple of degrees above absolute zero, it transforms into This stuff is incredible. A superfluid has zero viscosity, meaning it can flow without any friction at all. If you stir it will continue to swirl forever. It can defy gravity, crawling up the walls of its container and escaping. It can even seep through microscopic cracks that would be impassable for any normal liquid. It's like a liquid ghost, governed by the strange laws of the quantum world. So, while we can't reach the absolute bottom of the cosmic thermometer, our journey towards it has unlocked some of the deepest secrets of the universe. From the fundamental hum of zero-point energy to the ghostly dance of superfluids and the collective consciousness of a Bose-Einstein condensate, the world near absolute zero is a bizarre and beautiful quantum wonderland. It shows us that even in the most extreme cold, the universe is far from dead. It's alive with a quiet, persistent quantum energy that makes everything we know possible. It's a reminder that even at the point of ultimate stillness, there is still motion. What do you think is the most mind-blowing thing about absolute zero? Let me know down in the comments. Thanks for joining me on this chilly adventure into the quantum realm. If you enjoyed this video and learned something new, do you want to forget to hit that like button and subscribe for more deep dives into the wonders of science? See you in the next one.